In this final video for Chapter 10, we're going to look at the slight adjustments we have to make to the naming rules for naming cycloalkanes. So let's focus on the differences. First of all, we add the prefix cyclo in front of the name of the parent hydrocarbon. So for example, if the parent hydrocarbon was butane, that is 4 carbons, and they were found in a ring, it would be called cyclobutane. If there is only one substituent on the ring, then there is no need to put a number on that substituent. It's automatically carbon 1, no matter how it's drawn, if there's only the single substituent. If there are 2 substituents on the ring, we give number 1 to the substituent which occurs first alphabetically. So given the choice between ethyl and methyl, ethyl would be the one which is number 1. And if there are 3 or more substituents, we number so that we get the lowest possible numbers. So let's go ahead and take a look at these compounds. And rather than pause the video, we're just going to go ahead here and name them. So our first compound here on the left has a ring with 6 carbons in it. So that would be hexane, but since it's a ring, it's cyclohexane. There are 2 substituents, so we want to give number 1 to the substituent whose name comes first alphabetically. So this group down here is a methyl group. What is this group here? 3 carbons, and it's attached to the middle carbon, so that's called isopropyl. So alphabetically, isopropyl comes before methyl. So this is going to be 1, and we're going to number to get the next number as low as possible. So 1, 2, 3. So it will be 1 isopropyl, 3 methyl cyclohexane. In the next compound, since there's only 1 substituent, that automatically makes this carbon number 1 right here. And so we don't have to number in the name. We'll just say ethyl, and then the name of this group here, which is cyclopropane. Again, it's cyclopropane because propane is 3 carbons. This is a ring of 3 carbons. Ethyl cyclopropane. And in this final molecule right here, we have 3 substituents, and they are all the same. They're all methyl groups, so it's going to be trimethyl something. If we number starting with this methyl group, it would be 1, 3, 4. If we number here, it would be 1, 3, 4. But if we start with one of these, we can get the number down even lower. So this would be 1, 2, 4. And that's how we're going to name this. So it's going to be 1, 2, 4 trimethyl, and then cyclopentane, a ring containing 5 carbons. The main use of hydrocarbons with which most people are familiar is their use as fuel, for example, in combustion reactions. So let's think of, for example, natural gas. Natural gas is mostly methane, and it can be burned for fuel. Oil, petroleum are primarily composed of hydrocarbons, and coal as well is primarily hydrocarbons, although with significant amounts of impurity. So these are all mixtures, coal and petroleum, and what we need to do when we're trying to get good useful fuels out of these is to separate the mixtures. And so the technique that we use is what is called fractional distillation. Now, the compounds that are in the mixture have vastly different boiling points. Recall that the compounds which have very few carbons in them are going to have very low boiling points, while the ones which have substantial amounts of carbon in them are going to have high boiling points. So what we can do is we can heat these up to separate out some of the different components in the mixture. So crude oil would be heated, and that would change everything into a gas. And then those gases can be put in a very, very large cooling tower, and that will separate them out by their boiling point, with the lower boiling compounds essentially traveling the highest up the cooling tower. And you've seen these kinds of fractionating columns before, I'm sure, if you've driven down, for example, the 405 freeway around, say, Carson, perhaps around El Segundo in the different cities that have oil industries in them. And you can see what happens here. We basically pump the crude oil, which comes out of the ground, into pipes. We substantially heat them so that they all vaporize. And then the lower boiling compounds go ahead and go up to the very top and go out as gases. And then the groups which have, say, for example, 6, 7, 8 carbons can be separated out into gasoline. The groups with a little bit more carbons into kerosene. And the groups that really don't vaporize well at all remain towards the bottom as tar. While there certainly are some useful reactions of alkanes, compared to all the other different functional groups we have, they are relatively unreactive. And the only reaction I'm going to consider here is combustion reaction. A combustion reaction is simply a reaction with oxygen. And whenever we take a hydrocarbon and react it with oxygen, it will form carbon dioxide and water. These reactions are always what we call exothermic. They always release heat. So let me give some examples here with some formulas. First, let's consider the combustion of heptane. So the reaction would be heptane, and then we write plus oxygen, give an arrow to form carbon dioxide and water. So this part never changes. It's our compound plus oxygen gives you carbon dioxide and water. So here is heptane, C7H16, plus oxygen gives you carbon dioxide and water. And of course the 11, the 7, and the 8 come as a result of balancing the equation after it's already been written. How about the combustion of butane? Butane, you'll recall, is C4H10. It's found in cigarette lighters. I would encourage you to take a moment and pause the video and attempt to write the combustion equation for this. It's something you should be able to do. So again, butane is C4H10. And now I'll go ahead and put up the equation. So it is C4H10 plus oxygen, O2, gives you carbon dioxide and water. And the balancing is a little bit complicated on this one. So we have 2, 13, 8, and 10. And recall, as I said a moment ago, that heat is given off on all of these. However, since heat is not a chemical substance, it's not shown in these reactions. This will conclude the lectures for Chapter 10.